Review for a final exam. In number one, we have some limits, different types of limits. So let's look at part A. In part A, we have the limit as x goes to infinity of this rational function. So we know that the limit as x goes to infinity is equal to the limit as x goes to infinity of the highest order term in the numerator divided by the highest order term in the denominator. So this is equal to the limit as x goes to infinity of 6x to the 7th divided by 2x to the 6th. And we'll reduce that. And we have simply 3x. The limit as x goes to infinity of 3x, and that's equal to infinity. Now let's look at the limit as x goes to 6 of the square root of x minus 2 over x minus 6. Notice if we substitute in 6 into the denominator, we have 0. And if we substitute 6 into the numerator, we have 6 minus 2. We have the square root of 4, which is 2, minus 2. So that's also 0. So this is what we call a 0 over 0 limit. And usually in this situation, we try to reduce and then take the limit. So what we want to do is we want to basically reduce this, and we don't see an x minus 6 in the numerator that could cancel with this x minus 6 in the denominator. So we're going to manipulate the expression by multiplying top and bottom by the conjugate of the numerator, that is by square root x minus 2 plus 2. Okay, so here in the numerator, since we have conjugates, that is a minus b, a plus b situation, the middle terms drop out, so we only have to do first last in the FOIL multiplication. So first we have root x minus 2, root x minus 2, that is equal to x minus 2, and minus 2 times plus 2, that is equal to minus 4. And in the denominator we have x minus 6 multiplied by the square root of x minus 2 plus 2. So notice in the numerator over here, x minus 2 minus 4, that's equal to x minus 6. And we'll cancel that with this x minus 6 in the denominator. So we're left with the limit as x goes to 6 of 1 over the square root of x minus 2 plus 2. And now if we substitute in 6, the denominator is no longer equal to 0, so we can just substitute right in, and we get 1 over 6 minus 2 square root of 4 plus 2, that is equal to 1 over 2 plus 2, or 1/4. In part C, we have another 0 over 0 limit. If we substitute 3 in the numerator, we get 0. And in the denominator as well, if you substitute in 3, we have 9 minus 15. That's a negative 6 plus 6, which is 0. So it's another 0 over 0 limit. So we're going to try to reduce like we did in the previous example. So we're going to factor the denominator this time. That factors into x minus 3 times x minus 2. And we have this x minus 3 in the numerator, so we can just cancel these. And now we can take the limit by simply substituting in 3. So let's do that. So we have 1 over 3 minus 2, and that's equal to 1. In part D, we have a piecewise defined function. To the left of 3, we have the expression 3x plus 2, and to the right of 3, we have 2x plus 1. So in order to take the limit as x goes to 3, we are going to use the top expression if we're approaching from the left, and the bottom if we approach from the right. So we're going to take first the limit as x goes to 3 from the left of our function, and that would be obtained by simply substituting 3 into this expression. 9 plus 2, so we have 11. And now let's take the limit as x goes to 3 from the right of our function, and limit from the right is obtained by using this expression. So we have 2 times 3 plus 1. 6 plus 1 is 7. Well, since the limit from the left is not equal to the limit from the right, that implies that the limit as x goes to 3 of our function does not exist. In part E, we have a one-sided limit, the limit as x goes to 5 from the left. And when we approach 5, the denominator, if we substitute in 5, the denominator is 0. The numerator is not 0. This is not a 0 over 0 limit. This is what I would call a 1 over 0 limit, meaning non-zero over 0. And this type of limit is equal to either 1 or either infinity or minus infinity. So we basically have to decide, is it infinity or minus infinity? Okay, so what we do is a plus-minus analysis on this expression, x minus 3, x minus 1, x minus 5, and we put on the number line, we place the zeros of the numerator and denominator. So those would be 1, 3, and 5. Okay, at 1 I'm going to put an open circle because it comes from the denominator. At 3 a closed one. And at 5 another open one. Now we're approaching 5 from the left, so that's from numbers less than 5, so that's here to the left. So we really just want to see on this interval, is this expression positive or negative? So let's substitute in a value like 4, for example. So if we do that, here we have 4 minus 3, which is positive, 4 minus 1 is positive, and 4 minus 5 is negative. So 1 negative. So that would mean that on this interval, our expression is negative. And we already said that this is a 1 over 0 limit, so it goes to either infinity or minus infinity. Since it's negative here, that means that this limit is equal to negative infinity. Now, in part F, in order to do this limit, we first are going to rewrite this expression, absolute value of x minus 5 over x minus 5. So here we go. This is equal to, let's just see what this is equal to. If we remove absolute values, well, we have two cases. Let's first look at the case where x is larger than 5. If x is larger than 5, the top is positive and the bottom is positive. So this expression is equal to just x minus 5 over x minus 5, which is 1. Now, let's say x is less than 5. Then x minus 5 is negative. And so the absolute value is positive. And here we have x minus 5, which we said is negative. So in this case, the quotient is equal to, I'm going to write it out, it's equal to x minus 5 in the denominator, and we said x minus 5 is negative, so in order to get the absolute value, we'll negate it. So what we have is we have minus x minus 5 over x minus 5, which is equal to minus 1. Okay, so this is equal to limit x goes to 5, and we have the following. We have a function that's equal to 1 when x is less than 5, and, minus 1 when x is less than 5, and 1 when x is greater than 5. Okay, so if we take the limit as x goes to 5 from the left of our function, we simply have minus 1. And the limit as x goes to 5 from the right of our function is equal to positive 1. And again, these are not equal, so we conclude that the limit, therefore the limit as x goes to 5 of our function x minus 5 over x minus 5 does not exist. Here we have another limit as x goes to infinity of a rational function. So we only need to look at the highest order terms, numerator and denominator. So we say this is equal to the limit as x goes to infinity. Here's the highest order term in the numerator divided by the highest order term in the denominator. All right, let's just reduce that, and we have 5 over 4x. So the denominator is going to infinity, and the numerator is 5. So basically, this is what I would call a 1 over infinity limit. 1 over infinity limit is always equal to 0. Now, this last limit is based on the following limit that we saw in class. In class, we saw that the limit as x goes to 0 of sine x over x is equal to 1. So we're going to use this to find this limit. And what we do is we just sort of manipulate this into something close to this limit. Let's look at the limit as x goes to 0 of sine 3x over 3x. And here's sine 7x over 7x. Okay, now these two are not equal. The x's cancel, but we have a 7 here and a 3 here. So to make up for that, let's multiply by 3 over 7. Now these two expressions are equal. 7 over 3 cancels with 3 over 7, and the two x's cancel. And we did that because since this goes to 0, sine 3x over 3x also goes to 0. So this piece, goes to 1. Goes to 1. This piece goes to 1. Now, since this is true, the reciprocal also goes to 1. So here we have the reciprocal. This also goes to 1. So we have this piece goes to 1, and so does this. So what we're left with is 3 over 7. So our limit is equal to 3 over 7.